Hi, today we will talk about how to find the area of some regions defined by one or two graphs. This is also application of definite integration. Let's get started. Area. There's a graph of function f of x, and I'm going to make an area, a region. This line is x equals a, the other line is x equals b. We are looking for area of this region. You guys already learned about Riemann sum, right? Use definition of Riemann sum. So the area should be between a and b f of x dx. We use dx, right? So interval a and b, upper interval and lower interval, both of them are in terms of this letter, x, right? Based on function f of x. So finding area is kind of easy. Next case. Graph is like this. That's f of x. And x equals a is here and b is here. We are looking for the area of this part. If we use exactly same definition of definite integration, it's going to be area should be integral from a to b f of x dx, right? But this is value. If you actually calculate this value, which is integration, should be negative because the region is under the x-axis. That should be negative, but we are finding area, so area should be positive, right? So you put absolute value sign and make the area part, value of the area positive, okay? All right, next case. Now we're going to find the area between two graphs. That's first one, which is f of x. This is second one, g of x. And their intersection point is a and b. And you are looking for the area between two curves. The answer is this. The area between two curves is, you need to find the area under the curve of f of x, because f of x is above. So you find f of x first, which is like this region, right? That's A, that's B. Minus from a to b, g of x dx, which is graph G is like that, and a and b, right? That expression, integral from a to b g of x dx, means that one. So this part minus that part is this part, which is the area of the region that we are looking for. Algebraically, you can combine them. So area of the region is from a to b f of x minus g of x dx using one integral sign. It's possible. You can combine them because they do have same intervals. Okay? But we can think of a little bit different case. What if sum of the area between two curves is under the x-axis? Like this. That's f of x. And then this is g of x. So, yeah, x equals a is first intersection point, x equals b is second intersection point. We are looking for the area between two curves, like that. This part is okay because they are positive, but this part is negative. The blue part is negative. How can you find the area? Do you have to find the area of this negative reason and put absolute value sign? It's pretty hard. So in this case, let's apply vertical shift. Vertical shift. Let's move f of x and g of x, both of them move up by like 500, very big number. So if you move them up by 500, you can keep same area. But because you moved both graph up by 500, which is a very big number vertically, x-axis should be here. This is x-axis. So both curves are above the x-axis. You can take this part as positive. That's positive part. So the answer should be like this. Area of the region is integral from a to b f of x plus 500 minus g of x plus 500 bracket dx. Inside the integral, you can simplify. 500, negative 500 canceled out. So what is left? Just f of x minus g of x dx, which is same as the original case, previous case. So we can conclude that every time you find the area between two curves, you just use subtraction. Subtract lower curve from upper curve. Okay? Yeah, then we can guess another case about finding area. X and Y. Yeah, this is f of x graph. And we are looking for the area of the region between A and B, like this. This is different case because interval is given in terms of y. That's y equals A, and this is y equals B. Then how can you find the area of the region? This is what we are looking for. Yeah, to find the area of this region, let's place small rectangle like this. This is also application of Riemann sum. I'm going to place this kind of rectangle from A to B, like that, from A to B. Let's find the area of this rectangle. And what is height of this rectangle? Height should be very short vertical length. Very short vertical length, right? So we can use dy. And what is length or width of this rectangle? Should be x value, right? This length of this rectangle is x value of the curve. X value curve of f of x. So I will use x of c, x of the curve. So how can you find the area of this rectangle? Length, x of the curve, and then width or height, dy. That's the area of the rectangle. And I'm going to add areas of this kind of rectangle from A to B in terms of y. So the area that we are looking for is from A to B, x of the curve, dy. Finally, we need to change x of the curve to another expression in terms of y. Why? Because everything else is in terms of y. We use dy and inverse are in terms of y. So you can't use x. So you need to change x to another expression in terms of y based on the given function. Let's say given function f of x is e to the x power. So y is e to the x power. You isolate x, put ln on both sides. ln y is equal to ln e to the x power. Based on the logarithm property, you can move this to the front. So x times ln e equals ln y, and ln e is equal to 1, right? So x equals ln y. This x means x of the curve. So for x, you can use ln y. You replace x of curve with ln y. So finally, we can use this. You need to simplify it. Okay? All right. These are basic concepts of how to find the area of the region defined by one or two curves. Next time, we're gonna try actual questions.